today's video, I will walk you through a gray to binary code converter implemented in system Verilog. Gray code and binary code are fundamental to digital systems, and converting between them is an important process in error detection and correction. Let's dive into how this conversion works and the logic behind it. Before we start, let's quickly recap what is gray code and what is binary code. Gray code. Gray code is a binary numeral system where two successive values differ by only one bit. This makes it useful in systems where errors needs to be minimized, like in digital communication. Binary code is a standard form used by computers where each bit represents a power of 2. Now we are going to design a system that converts a 4-bit gray code input into its corresponding binary code output. Let's now look at the design of our converter. Here is the system Verilog code for the gray to binary code converter. We begin by defining a model in system Verilog called gray to binary. This is the name of the code. This module will perform the conversion from 4-bit gray code to binary code. Input logic 3:0 gray code. This line declares a 4-bit input signal called gray code. This is the input gray code that we want to convert into binary. Output logic 3:0 binary code. This declares a 4-bit output signal called binary code. This is where the converted binary code will be stored and output from the model. Always COM begin. This is a system Verilog block that defines the combinational logic. The always COM block automatically triggers whenever any of its input signals change. In case if gray code changes, this block will execute to calculate the corresponding binary code. In the next line, we are directly assigning the most significant bit MSB of the binary code to the MSB of the gray code. Why in gray code the MSB is the same as the binary MSB? So no conversion is needed for this bit. For example, if the input gray code is 1001, the MSB of both gray code and binary code will be 1. For the second bit, binary underscore code 2, we use an XOR operation between the MSB of the binary code and the second bit of the gray code. Why XOR? Gray code is constructed in such a way that each successive bit changes based on the previous binary bit. The XOR operation helps in determining how each bit changes relative to the previous one. So if gray underscore code 2 is equals to 0 and binary code 3 is equals to 1, the XOR operation will give 1 as a new value for binary code 2. For the third bit, we again use an XOR operation between binary code 2 and gray code 1. Why this step? Each subsequent bit in binary code depends on the value of the previous binary bit and the current gray bit. The XOR operation is used to calculate how the binary bit transitions. For example, if binary code 2 is equals to 1 and gray code 1 is equals to 1, then XOR operation will give 0 for binary code 1. Finally, for the least significant bit LSB, we apply the XOR operation between binary code 1 and gray code 0. This bit is calculated in the same manner as the previous ones. The LSB of the binary code is determined by comparing the previous binary bit with the LSB of the gray code. Here, the always COM block ends here, marking the completion of our logic for converting gray code into binary code. We then close the module with end module. The conversion logic is now fully defined and ready to be used in digital systems. Let's now see the test bench code. We start by declaring the test bench model named TB gray to binary. The TB prefix is commonly used to denote a test bench module. Signal declaration. Logic 3:0 gray code. This declares a 4-bit signal gray code which will be the input to the gray code to binary converter. During simulation, we will assign different gray code values to the signal. Logic 3:0 binary code. This is the output signal for the binary code that will be produced by the converter. The binary code will hold the result after the gray code is converted, instantiating the converter module. Gray to binary UUT. This instantiates the gray to binary converter module we designed earlier, named it UUT, which stands for unit under test. We connect the gray code input of the test bench to the gray code input of the converter and the binary code output of the converter to the binary code signal of the test bench. Gray code connects the gray code input signal. Binary code connects the binary code output signal. Initial block. This initial block is used to define a sequence of events that should run once during simulation. This block runs automatically when the simulation begins. Display and monitor statement. This display command outputs text at the start of the simulation. In this case, it prints gray code, binary code as a header for the output to make it easier to read. Monitor. This continuously monitor changes in the signals. Whenever the gray code or binary code value change, it prints their value in binary. It shows the gray code input and its corresponding binary code output, helping us track the conversion as we run different test cases. Test cases. These lines represents the different test cases for the gray to binary code conversion. Gray code is equals to 4 bar B0000 hash 10. This applies the gray code 0000 to the converter, waits for 10 time units and then moves to the next case. Each subsequent line sets a new gray code value, waits for 10 time units and record the output. This approach helps us verify if the converter is working for the wide range for gray code inputs. For instance, gray code is equals to 4 B0000 is expected to be converted to binary code is equals to 4 B0000. We cover all 16 possible combinations for 4-bit gray code. Finish the simulation. Finish this command terminates the simulation after all the test cases has been processed. Without this, the simulation would continue running indefinitely. End. This marks the end of the initial block. End module. This marks the end of the test bench module. Part of the test bench code is dump VCD file. Without dump file, we cannot generate output waveform. This file records changes in the signal values over time during the simulation. It is particularly useful for analyzing the behavior of your design as you can visualize the signal transitions in waveform viewers. Dump file gray to binary code.vcd. This command instructs the simulation to create a VCD file named gray to binary.vcd. The VCD file will store the values of signals throughout the simulation, capturing the changes over time. It's important to name the file appropriately as it will help you to identify it later when you want to analyze the simulation results. Dump vars tp gray to binary. This command specifies which variables to include in the VCD file. Dump vars 0, tb gray to binary means that we want to dump all the variables defined in the test bench. The 0 indicates the level of hierarchy in the design. 0 means to include all variables at the current level of hierarchy. By dumping all variables, you capture the value of gray code, binary code and any internal signals or states during the simulation. The output waveform for the gray to binary code converter. In this waveform, we have two main signals. Binary code 3:0, this represents the 4-bit binary code output. Gray code 3:0, this represents the 4 binary code input. The goal of this converter is to transform the gray code, which changes only 1 bit between successive values, into corresponding binary code. The gray code signal shows a sequence of a number which is gray code, for example 0, 1, 3, 2, 6, 7, 5, 4, etc., which is how the gray code pattern progresses. The binary code shows the corresponding binary values for each gray code. The sequence continues in a predictable manner. This waveform shows how a gray code sequence is being accurately converted to binary code over time. For each gray code value, the converter produces the correct binary equivalent. This is crucial in applications where reducing transition errors is important. Thank you.